first of all my co-authors, Andrea Carpentieri and Sabrina Vantadori from the Department of Civil and Environmental Engineering and Architecture in Parma. So, speaking about civil engineering, the topic I would like to talk about today is related to some building problems, and in particular I'm focusing on some problem related to the cladding of buildings made by natural materials. So these materials are characterized by quasi-brittle behavior in fracture, but in comparison to concrete material, they have been much less investigated. So I'm trying here to show some experimental results and some interpretation of these results using multi-parameter approaches. So, what is the motivation of the study? As I said before, we are interested in some problems related to the cladding of buildings. In particular, we were studying some ventilated facades where the slabs used were made by natural stones, and in particular marbles. So these elements are subjected to a number of different actions, which include temperature variation, daily and seasonal, mechanical loads, as well as chemical and humidity changes. These two buildings were the one we were involved in the study, and they were covered by two different kinds of marbles. The one on the left is a white marble from Carrara, and the one on the right is a red marble from the area of Verona. So with this motivation, we wanted to investigate the fracture behavior of these two materials. Well, this is just some technical aspects of the cladding system related to the boundary condition of the slab. So there are different anchorage systems, and so some of them are characterized by Pointwise anchorage, whereas in some cases there are lengthwise anchorage. The dimension of the slabs are of the order of tens of centimeters, and the thickness, typical thickness is of 2-3 centimeters. So speaking about the white Carrara marble, one of the main concern of this of the application of this material to building cladding is the deformability. So one aspect that it was experienced in these two famous buildings, for instance, but there are other cases reported, is bowing, which is a phenomenon of a permanent deflection of the panels due to related to the thermal excursion of these panels. The one on the left is the Amoco building in Chicago, where you can see that there are indication of bowing of the order of more than 30 millimeters in panels of the size of about 1 meter. And the one on the right is the Finlandia Hall in Helsinki, again with more or less the same size of bowing. And in both cases you can see the thickness of these panels is about 3 centimeters. In the case of the Verona marble, instead one of the most frequent problems is related to the strength of the material itself, and there are experience of cracking and some surface detachment of the material, and so this is a problem mostly related to the strength and more specifically to the fracture toughness of the material. So these two, for these two kind of marbles, we wanted to perform some investigation, starting from the some microstructural features, and then mainly on the mechanical testing. So white marble is a metamorphic rock, and is at the microstructure level is characterized by grains of calcite. And here on the left you can see two pictures. The one below is obtained with a polarized light, and in this way you can detect the orientation of the grains. The size, here well, you have a distribution of the grain size, and the average on the specific marble that we investigate is about 200 microns. As for the orientation of the grains, there is some important characteristics related to the thermal deformability of this material, of these grains of calcite, which is anisotropic, and this was investigated in some previous work of ours, where we built a model to describe this anisotropic thermal behavior, and to relating this behavior with the overall bowing of the marble slabs. When you go to Verona marble, instead we have, it's called marble again, but it's actually a different kind of rock. In fact, this is a sedimentary rock, and when you go into the microstructure characterization, you see a very different features. In fact, there are a large amount of organic phases related to thin-shelled bivalves, and the matrix of microcrystalline calcite is of the order of the size of about 5 microns. So the features of the material in this case is much more refined, and it's also much more with different characteristics and, let's say, multi-phases in the material. So, as for the experimental test, we first of all had of course, the tensile strength from bending testing, and what I want just to mention here is that the mean value of the strength, which is quite similar in the two marbles, but what you can see in the case of the red Verona marble, you have a much larger scatter of the results with a coefficient of variation of about 0.3. And this can be attributed to the fact that there is an heterogeneity in the material, and for instance, these are two results where you can see the fracture surface on the left. There is what corresponds to a much lower tensile strength in comparison to the one on the right. So I'm picking here two extreme cases, and the lower bound is related to some weak phases in the material, which is due to some clay inclusions in the texture. So the main focus is on fracture test, and we perform a 3-point bending test of an edge notch beam. So these are the 6 results for the white Carrara marble and the right 7 results for the Verona marble in terms of the nominal stress versus the crack mouth opening displacement. What we can see from the very beginning it's clear that there is a non-linear behavior prior to the peak load, identifying clearly this so-called quasi-brittle behavior. So these curves are pretty similar to the curves that you can find for concrete, but as I said at the beginning, there is much less experimental data available in the literature for these natural materials. So what we start with at first is to have a calculation of the toughness based on linear elastic fracture mechanics from the initial notch length, and these are the two values, mean values that we work out for the two materials, and they are pretty close. And what we can see clearly that if we represent the data in a plot of a nominal stress adjusted by the relative notch depth versus the initial notch length, you can see that the trend of the results is not following the linear elastic fracture mechanics, so as expected. So what we wanted to show here is to show how we could use different approaches based on further parameters to describe these experimental results. So the quasi-brittle behavior is related to a finite size fracture process zone, which is ahead of the crack tip, and this is characterized by a certain length L. So depending on the size of the ratio between the characteristic size of the structure and this length L, you might have a non-linear behavior and a size effect. So one of the very first models using the concrete community to describe this quasi-brittle behavior is the cohesive crack model by Hillerborn, which needs the use of two parameters. One is the tensile strength, Ft, and the fracture energy, Gf. And so this, I mean, there are many many papers in the literature on this Hillerborn paper, and there are refinements on the theory. What is very important is the cohesive law, and for instance, it's very relevant the initial slope in the sigma W curve. And so, for instance, Plan has proposed to use 3 different parameters to describe the cohesive crack behavior, and one is related to the initial slope of the sigma W curve. So here I'm just mentioning many other theories that can be related to multi-parameters to describe fracture toughness. There are the size effects laws by Vajant and Carpinteri. There are some the crack extension resistant curves. There is the finite fracture mechanics theory of Taylor's and co-workers, and there are non-local stress failure criteria, and the theory of critical distance, just to mention a few. All of them make use of some additional parameters for giving the fracture resistance of the material. When you use linear elastic fracture mechanics, you have to adapt the theory to add some additional parameter. And so, if you consider the fracture process zone, one way to deal with this adaptation is to consider some distance, delta A, which is extending the traction-free crack length into the fracture process zone. This, of course, implies the fact that you have some non-zero crack tip opening displacement. And so what we are just what we try to do is to use the specific model by Shah from the Northwestern University, which is a two-parameter model, which makes use of a critical value of crack tip opening displacement. And this becomes the additional parameter for fracture resistance description of the behavior. So this parameter needs to calculate, it makes still in the framework of linear elastic fracture mechanics, but calculate this increment of the initial crack length A0, so calculates this delta A through the compliance, which is the crack mouth opening displacement divided by the load. The former is measured from the experiment to the click gauge. And okay, so these are the results, two curves from the results that I showed you before. And so from the initial compliance you work out the Young modulus, then from the failure compliance you obtain the effective crack length, and from the effective crack length you work out the effective toughness. And finally you can have a measure of the blunting of the crack, what is called the CTOD critical, and eventually the length parameter Q can be calculated. So just a couple of slides. So these are the results in terms of mean values and standard deviation for the two marbles that I show you. So the columns in red is related to the nominal toughness that I showed you before, and the one in blue column is the effective toughness using these two parameter model. Plus there are the delta A, the increment of the crack to obtain the effective crack length, the crack opening displacement, and this length parameter. The main points to discuss here is that the fact that the Verona marble show a significant increment of the initial crack length up to collapse. This is about 20 times the mean grain size in the material, and the parameter Q is on average equal to 40 millimeters. In the Verona marble instead we have a smaller increment of crack, which is much higher than the mean microstructural size, but what I said before, in the case of the Verona marble, there is no such a regular microstructure of the material, and the Q parameter is on average about 15 millimeters. So what at least we can say from the results is that there is a trend between the delta A, the increment of crack length, versus the material microstructure. And so these are
we can just leave it there.
Okay. Let me finish with the tube diaphragm, and by the way, the toughness was made by red Verona marble that is standing for 800 years. So, yeah.
Okay.